So I wanted to kind of pick up where we left off. We were looking at these last couple of molecules on your worksheet at the bottom. And we had talked about the suffixes that we give based on different functional groups. So far, what functional groups have we decided will be indicated in a compound by the suffix or the suffix stopper? What functional groups show up there? Alcohol shows up. Is alcohol a suffix or a suffix stopper? Right. So if an alcohol is present, and this is our highest priority functional group, if an alcohol is present, we always stopper the suffix with OL. What other functional groups are indicated, their presence is indicated by the suffix? And alkanes. All of our hydrocarbons. Alkanes, alkenes, alkynes. Carbon-carbon single bonds, carbon-carbon double bonds, carbon-carbon triple bonds. And we can stopper, replace the E at the end of these names. We can stopper that with OL. Ane is the only one that is never compounded with the others. But alkene and alkyne, if they're both present in a carbon chain, they can both show up in the nomenclature as kind of like a double suffix. I want to point out that we gave the prefix, or sorry, this generic form for what nomenclature would look like. And we said that we'll take the root and we'll put this locant in before we show the suffix and the suffix stopper. So our structure on the left, we decided that the parent chain was the longest carbon chain that included the highest priority functional group. And the alkene was the highest priority functional group. So we didn't look for just the longest carbon chain. That would have been the 7 carbons going across the bottom. Instead, we went for the longest carbon chain that included the alkene. So we counted a 5 carbon chain. And did I say that wrong? Yeah, it's not 7 carbons along the bottom, it's 6. We counted a 5 carbon chain that included the alkene. And that we'll call our parent. So we gave it the root, pent, and we gave it the suffix ene, but we didn't actually clarify a locant. With this 5 carbon chain, I could place the carbon double bond of the alkene at a lot of different positions. Here, I can actually say that the carbon-carbon double bond, the alkene, starts at position 1. And so the locant is used as a positioning along the carbon chain. A lot of times, though, the names take this locant and they'll put it in front of the root. So this might be called 1-pentene instead of pent-1-ene. Both are acceptable. We also decided that this name, 1-pentene or pent-1-ene, it doesn't actually describe everything that's happening in the structure. There's a 2-carbon group that is not a part of this longest continuous chain. So to describe 2 carbons, we'll give this the root eth, and we'll give it a suffix yl. Do you guys remember what we decided the yl suffix informs about something? It's a substituent. YL means that it's not part of the parent chain. YL means that it's a substituent. This is a 2-carbon substituent. And this becomes our prefix, along with its position in the chain. And so the prefix that comes before root, the prefix often contains its own root. how long that substituent is, and its own suffix, this YL, that tells you that it is a substituent, not part of the parent. The prefix also often comes with its own locant. So combining the fact that this has an ethyl substituent and the alkene is located on the first carbon, we keep this numbering system starting at the alkene, and we see that the 2-carbon group comes off of position 2. We get a full name, 2-ethyl, 1-pentene. Two-ethyl counts as the prefix. That is the substituent. That's what's coming before everything about the parent chain. 1-pentene is just telling us about the parent chain. Good. The 2 here is the locant where the ethyl connects to the parent chain. Perfect. You'll also notice we're using these hyphens. Hyphens will separate locants from anything else. We're going to get into examples that have multiple locants. And so we'll have to describe using commas separating locants from each other. Okay. This is our segue into prefixes and substituents. I've given you this first structure not so much to name it, but to introduce you to some of the more common substituent groups that I want you to be familiar with. When bromine and chlorine are substituents on your carbon chain, we put them in the prefix as bromo and chloro. As we go around this ring clockwise, I'm listing out the common substituents in alphabetical order. And I want to point out the alphabetical order because when we start putting a full name together, we'll organize all of the different substituents alphabetically, regardless of what their individual locant is on the carbon chain. So bromo, then chloro, and I screwed up my alphabetical order. Dang. Okay, so the idea was alphabetical, but there is a typo. A 2-carbon chain we already discussed is given that prefix ethyl. When I have a 4-carbon substituent that consists of 3 methyl groups connected at this central carbon, we'll refer to this as a tert-butyl group. And we can spell that out, tert-butyl, or we can list it as T-butyl. Tert is meant to reference a tertiary carbon. The carbon of this 4-carbon group that connects to the parent chain, that carbon is connected to the other 3 carbons of the 4-carbon group. It's a tertiary carbon. Except that it's not a tertiary carbon. In this example, would you agree that this carbon has 4 bonds to other carbons? So it's a quaternary carbon, but it's a tert-butyl group. Yeah, I don't like it much either, but it's just the way that we describe it. This is a 3-carbon chain, and it's connected at the central of the 3 carbons. We can't call this propyl in thinking that it might just be a linear chain. Instead, we give this the name isopropyl. And you'll notice these similar groups that all have iso at the start, and then they end with 2 methyl groups off of the last carbon. There's an isobutyl form and an isopentyl form as well, but isopropyl is the one that you'll see the most commonly. And then I've got this 1-carbon chain. This is methyl. Here's where I screwed up in my alphabetical order. Bromo and chloro obviously are alphabetized by B and C. Ethyl and methyl are alphabetized by M. But then these other 2 names, which aren't just the number of carbons in the chain, but describe a little bit more about the chain as well. Isopropyl is considered a common name, and so it gets alphabetized by I. Tert-butyl is considered a systematic name. It's describing the substitution of the carbon, so it gets alphabetized by B. The tert is descriptive of the name butyl, so butyl is how it gets alphabetized. Iso is not descriptive of the term propyl. Isopropyl is just the name, so we alphabetize it by I. I'm not going to say I like it, but it is the rule that we follow because we'll be alphabetizing all of the substituents. So we need to recognize these two cases predominantly. Okay, a couple of other strange substituents that show up. This second compound, 5-membered ring, that has a CH2Cl group and a CH2CH2Cl. Again, we could just write this in bond line structure. A 1-carbon chain with a chlorine, a 2-carbon chain with a chlorine. Oh, sorry, I did screw up this is not the same chlorine that I gave you guys. It's not the same position. CHCl, CH3. These substituents are more complicated. These are substituted substituents. This is not just a methyl substituent off of the ring. It's a methyl substituent that now has a chlorine off of the ring. So we can name it as a substituted substituent. This group becomes chloromethyl. It's not just methyl, it's chloromethyl. But on the other side, we get chloroethyl. At that point, there are 2 carbons on the chain that the chlorine could be positioned on. So we can't just name it chloroethyl. We need to describe where on that ethyl chain is the chlorine attached. This is the chlorine I gave you, but the one I drew just before this with the chlorine off of the second carbon, those would be different structures, so we need to describe their different positions. Inside of parentheses, we'll describe that the chlorine comes off of the first carbon of the 2-carbon chain by calling it 1-chloroethyl. And by putting this entirely in parentheses, we can now also give it a substituent location. We can provide a locant to describe where along the chain it shows up. Brenna. Good. Yes. That's exactly what I wanted you to point out. Our attachment to the parent chain, our parent chain is the ring. So our attachment starts from the parent chain and numbers out away from that group. Perfect. Okay. The last thing about prefixes and substituents. When we identified the parent chain in class on Monday, we said that it is the longest parent chain with the highest priority functional group and the most substituents. So this last structure that we have is meant to show that you can have the same parent chain in a number of different directions, but they can give you a different number of total substituents. So I would like you guys to find the way to number this compound such that it gives the most substituents. I'll give you one. I want you guys to reason out the best way to number it. One way that I could number this is to start from the left and number to the right. I've made my parent chain, the carbon chain, from the left to the right. I could have started at this bottom point and moved up to the right, There's a lot of different places I could have started at an end and counted to another end. With this counting system, my locant set is 2, 3. I have a methyl substituent that it's attached to carbon 2 on my parent chain. And I have a tert-butyl substituent that's located on the 3rd carbon from my carbon chain. So I want you to find another way to number this that maximizes the number of substituents. There are ways that I can get more than just methyl and tert-butyl. Take 5 minutes, work with the people next to you, find the numbering that maximizes the number of locants.
Probably a bad question because I don't know the rules super well, and I was
It's okay.
confused in the pre-reading quiz. I'm like, oh, this is a section I don't really need to read. So you're asking to maximize the number of substituents, right?
Yep.
So can the parent chain only be a 1 by chance? Could you do
Oh,
that? Or
well,
like a 1, 2?
Our parent chain should be the longest carbon chain
Okay.
that maximizes. So I've given you a 5-carbon chain.
Yeah.
You can find more 5-carbon chains.
In here, yeah. Okay, I see what you're saying. And we want more substituents, so rework the 5-carbon chain to get more.
Yep.
I follow, okay.
Just number it differently such that there are more substituents coming off.
We were wondering, so substituents, is that like each of these is a substituent?
True. If we considered the parent chain to be the cyclohexane ring, then everything becomes a substituent to the ring.
Okay, I was gonna say, but it needs to have a parent chain.
Yeah, we'll always establish a parent chain. So here the parent chain was the 6-membered ring. Here the parent chain was the 5-membered ring. Here the parent chain will be a 5-carbon chain. That's our longest carbon chain. But the carbon chain I gave you has 2 substituents.
Okay.
There's a way to number it that you get 3 substituents.
Did you get 2 of the same substituent? Like,
Yeah, you can get multiple
like these
of the
two are
same.
methyls, and then this one's isopropyl.
Yes.
And then this is the 5. Okay.
And that's not that doesn't maximize it, but that is a good start.
Oh, okay.
Because that had more, but there's another with more.
Come off the same carbon
Mhm.
like this one? Does that work?
It does.
As separate ones?
They have the same nature, they're all methyls, but they are different. Yeah, they're unique.
Okay. Okay.
So you would count them as 2,
Mm-hmm.
not like 1 put together?
So you have found how many substituents?
4.
Good. Way to go.
That's a good question.
We have lots of questions.
Let me hear them.
So this is what we had talked about.
Like if
Yeah.
you're labeling this way. And
Perfect.
Does that like, so then that would be its own thing, that's its own thing, that's its own thing. And then
Exactly.
Okay.
2 4 methyl groups,
Good. No,
or not groups.
3 methyl groups. Because this counts as the parent chain.
Yes. So you would have, these ones are coming off of 4. So 1, 2.
Oh,
3,
oh,
4,
I see, I
5.
see.
Sorry, yeah. So you have, it would be 4 methyl, right? And you'd have 2 of those, or no?
Yeah.
Sure. Oh, we'll talk about how to name them.
Oh, okay.
Okay.
I'll tell you how to put them in the name.
I
Oh.
see. That would be-
But you have maximized the substituents.
Okay.
Perfect.
So that means that the tert-butyl group is not necessarily a priority.
Well,
Are there any priorities?
tert-butyl is considered an alkyl group. An alkyl priority, it's just a substituent. Yep. So we certainly wouldn't try to number it to get a tert-butyl group.
There are no functions on here.
That's right. That's right.
Are these real?
Definitely real.
Okay.
Good. So this is the one I gave you. This is basically the same as it. You just switch this carbon. And then these two are basically the same. You just switch which carbon you go to. So it looks like you are missing one. Oh no, this is the pathway. It looks like you only gave 3.
Oh, this
But these are 2 separate ones. It's 2 separate methyls. Yep. Well, there's something we'll have to clarify. Okay, so how many substituents were you able to find? If you numbered it starting from that same spot, but you start numbering up into that tert-butyl group, you can actually find 2 separate methyls, a third methyl, and an ethyl. There's another way that you can number it to get 3 substituents. One of them becomes this isopropyl looking group, and then you get 2 methyls. That's if you take the 5 carbon chain that goes along to the right. Okay, so these are all our substituents. You will notice that we have 3 methyl groups. So when we need to communicate about this, we'll use multipliers. In this case, our multiplier becomes trimethyl. I don't just have a methyl substituent, I have 3 methyl substituents. So we call it trimethyl. When trimethyl gets alphabetized, because again, everything in our prefix will go in alphabetical order. When this gets alphabetized, we'll alphabetize it by methyl, because we're still describing the methyl substituent. We are just informing that there are 3 of them. Okay, another question that's worth asking here is, which direction should I number this 5 carbon chain? The locant set that I got here had a methyl at 2, ethyl at 3, and 2 more methyls at positions 4 and 4. But if I start numbering from the top of this chain and I number backwards, the locant set that I have for the same compound has a methyl at 2, a second methyl at 2, an ethyl at 3, and a methyl at 4. These are what we call the locant set. It's just a list of every position that has something coming off of it. And every time something comes off of a position, it's listed. Which is why position 4 is listed twice, because there are 2 things coming off of it. And it's why position 2 is listed twice, because there are 2 things coming off of it. The locant set that we use, do you know it already? We go with the lowest locant set. And that does not mean adding together the numbers and seeing which one has the lowest value. We go with the lowest locant set at the first point of difference. Okay, so the lowest point of difference, well, between these 2 sets, the first point is 2. I have a locant at 2 or a locant at 2. The locant sets are not different at this first point. Do you agree? At my second point, I can either have a locant at 3 or I can have a second locant at 2. What's lower? 2. So the correct locant set, the correct way to number this compound, is to number it with locants 2, 2, 3, and 4. Britton.
Does it matter, so the 5th point, does it matter if you put it on that far left carbon or the bottom carbon?
No, it does not. That 5th carbon could go up, it could go down. either way you number it still gives you a methyl substituent at position 4. Okay, so once we have the lowest locant set, we alphabetize the name. I only have 2 types of substituents. I have ethyl and I have methyl. Ethyl comes first alphabetically. So this is 3-ethyl, 2,2,4 trimethyl, pent for my root, ane for my suffix. Notice how most of that name is just the prefix. And then this tiny little bit at the end is the root and suffix. Here's another cool thing about this compound. You can get the number of carbons out of this structure. Ethyl is 2 carbons. Methyl is 1, and I have 3 of them. And pentane describes 5 carbons. The chemical formula is stored inside of that name. So 2 plus 3 plus 5, this is a 10 carbon system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A good way to check that your IUPAC name actually agrees with your structure, just make sure that they're communicating the same number of carbons. Okay. What I want us to do with this next problem is try to find the best locant set for each compound, keeping in mind that our rules for priority stay true with the lowest locant set. So if an alcohol is present, it gets its lowest locant possible. Number in a way, starting from the end of a molecule, where you can get the longest carbon chain that gives that alcohol its lowest locant. Then the alkene or the alkyne gets lowest locant. But if a compound has both an alkene and an alkyne, which one should I prioritize? Prioritize either one, getting the lowest possible locant. But what if I number one direction and it gives the alkene the same number that the alkyne gets going the other direction? When in doubt, we go alphabetical. In which case the alkene is alphabetical before alkyne. And then again, the lowest locant follows the priority for alkyl and halo groups with no preference for either type. Ti goes alphabetical. So I want to give you guys the name for this strangely substituted compound. 2 substituents. Yeah, Annie?
Is it alphabetical as in alkyl would go first if there's both?
No, thank you for bringing that up. Alphabetical as in bromo before chloro.
Okay.
Oh, and I didn't even fix that problem I gave you guys. With our big cyclohexane, butyl, tert butyl, comes after bromo, but before chloro. That was the mistake that I put in here. Butyl actually should have come directly after bromine. Tert butyl comes before the chlorine. So that's where the Ti goes alphabetical. If I could give tert butyl or I could give chlorine, locant number 1, I give tert-butyl locant number 1.
And does this apply like across those three rules or just within like alkenes and alkynes? Does that make sense?
Yeah, so the problem is that the alkene and the alkyne are equal priority. A molecule that has,
But we're always going to prioritize the
if there's an alcohol,
alcohol first.
work to give that alcohol its lowest locant, regardless of how it affects the rest of the molecule. Yep.
And if there's not, then we move.
But if there's not, and there's just alkene or alkyne, focus on giving them, and if it's a tie going 2 different directions, then go alphabetically. And then it's the same thing for alkyl and halo groups. Just look for the lowest locant set. If there is no alkene, there is no alkyne, there's no alcohol, just get the lowest locant set for everything. And if you're not sure which direction to go because it gives the same locant set, give the lowest alphabetically, the lower locant set. Okay, so for this compound, 2 substituents that will go in the prefix. Is it obvious that on a ring, I could start wherever I want? On a chain, I have to start at the end of a chain and move to another end. In this case, I had a lot of different ends that I could start with. Some that were all the same, couples that were similar, but different ending points too. On a ring, I can start anywhere for my locant set. Chains, I have to go linear. Rings, I can start anywhere. So I'm going to number this so that I get a locant set of 1, 3. I'm either going to number from the right to the left, counterclockwise, or I'll number from the left to the right, clockwise. But I have 2 locant sets that are a tie. So I look at my 2 substituents. One is chloromethyl, and the other was 1-chloroethyl. Which comes first alphabetically between chloromethyl and 1-chloroethyl? Well, they both start with chloro, so that part is all the same, which means I'm really analyzing the difference between methyl and ethyl. So chloroethyl comes before chloromethyl, which means that I'll give my lower locant position to the first one alphabetically. So this is 1,1-chloroethyl. 3-chloromethyl. And what is my root and suffix? The parent part of the molecule? Cyclopentane. No alkene, no alkyne, no alcohol. So the suffix is alkane. And the root cyclopent. Cyclopentane. Such a long name. And what was most of that name? The prefix. It was just the substituents. That was it. This idea of multipliers we'll come back to in later chapters. We're going to come back and hit on nomenclature again. Multipliers can get put into the suffixes too. So you can have things like 1,3-diene, 1,4,6-triol. You can have multipliers that describe those functional groups in the suffixes as well. Okay, so for what I want you guys to do is just work on this top row. Ignore these bottom 2. Just work on this top row for the next 5 minutes. See if you can identify all of the locants, all of the substituents, their locants, and the parent chain. Start putting together the components for the names for these compounds. That was a good question. What does ME mean? Methyl.
Why is it written? Why wasn't it written on the other one?
We can use different ways. So this is to expose you to other ways that you'll see it. CH3 methyl. We can abbreviate CH2CH3 with ethyl. We can abbreviate isopropyl with this IPR. We can abbreviate tert-butyl with this TBU. So these are like nomenclature structural condensed combinations.
This ring, would you start at the 1 then? Because the CL would be alphabetical. Okay.
Good.
And this naming, is that correct? 1-chloro, 2-methyl cyclopentane?
Perfect.
Okay, that seemed easier than I thought it would be.
Nailed it.
Thank you.
Yep.
This is just chloro. No, because you just didn't methyl. So that would give you the this lowest. This one is 2-2. That would go. Give you the lowest. No, you do 1-1. Because you want them to. But I think you. But I thought if chloro shows before, why would you use like? So we're looking just at you and the period is. Because you want the lowest number at the lowest, or like the most at the lowest number.
Yes. You want a locant set
Okay.
that describes all positions to be the lowest possible, but you'll organize them in the name alphabetically. Yes, nailed it. The end of chloro?
Do you need to have something else aside from chloro, or would it be like 1-methyl chloro and then cyclopentane, like alphabet? Yeah, from the left.
Oh yeah. So what do you have so far?
1-methyl, 2-chloro. That's it.
Oh, well, first of all, that's not alphabetical.
But isn't a methyl an alcohol, or isn't methyl alcohol?
No.
No, it's not.
No, methyl is a one carbon substituent. Yep. So it would be 1-chloro, 2-methyl. That is, yeah, just chloro. But that's just your prefix, yeah? So then what is your root and suffix? Cyclopentane. Mm-hmm.
So I did this one wrong because I want the majority of substituents. So basically, I should have done 1, 2, 3, because I want it to be the longest possible.
Yep, you want it to be both the longest and have the most substituents.
I think that is the.
You're right.
Okay.
Yep, if you go straight across, you get the same chain length,
Right, and it's only 1.
but you just get one substituent.
Okay. Cool.
Good work.
I named that correctly. 3-ethyl, 2-dimethylpentane.
Close, but it should be 2,2-dimethyl.
Good call. Thank you.
Yep.
Or is this bigger? Is this bigger than
Bigger. Who cares what's bigger? Do you mean higher priority?
higher priorities? An isopropyl?
But if it's just a carbon chain and an alkyl group, then it's the same priority as it's just low priority. Correct, doesn't really matter.
So would you just go across?
So look for the longest carbon chain that has the most substituents.
Carbon 1, 2, 3.
Oh, I see it now. Yeah. There's different carbon chains that have the same number of substituents.
Well, I said by initially, so like by is 2, but then it's like alpha chemistry.
Do you know what? I don't know the answer when it gets to that part of the rule. I don't know what you do next.
I think you do. Okay, and then
Maybe we'll just name all possible names.
Oh, perfect.
there's got to be a rule to then.
No, I don't think so.
So if you can go like both ways this way, you can go 1, 2 or 1, 2. They'd be at the same. They're the same level, right? And they're the same. Would you go alphabetically at that point to make that one?
Yes. For the chlorine and bromine, you just move in a direction that one of them is going to win alphabetically. They're at a tie.
Okay, so do bromine.
Yep.
John, what about this fourth one? 4 bromo, 3 chloro, pentane. Did I name the end correctly? Because it's not a loop. Like a,
Yes, it is a pentane,
Okay.
but you haven't named the 2-methyl,
Oh my gosh.
and that would actually come,
Before.
it would come after all of these.
Okay.
But because of that, I could get bromine to be at position 2. So there's going to be a tie, 2, 3, 4. So let's number it so bromine goes
I
first.
see. Okay. Thank you.
Yep. Wow, screwed that up a lot. All right. So, what I hope you were able to learn, starting with the rings, if you've only got those 2 substituents, then you get to start on one or the other, and your lowest locant set should be 1 and 2. That just means you're going to tie, and you should start with the lowest alphabetically. So we'll start at chlorine and call it 1-chloro 2-methyl cyclopentane. As soon as you change that structure and you add a second methyl group, especially to the same position, you now change how the preferred locant set will be acquired. Here I want to start at position 1 where my 2 methyl groups are. That's going to give me a locant set of 1, 1, 2. If I start where my chlorine is and number counterclockwise again, I get a locant set of 1, 2, 2. And 1, 1, 2 is lower at the first point of difference. Now, alphabetically, chloro and methyl still show up in the same spot. So I get 2-chloro, 1, dimethyl. I have picked the locant set that gives me the lowest locant set at the first point of difference. Alkyl groups like methyl, alkyl groups, and halogen groups all have the same priority. So I'm not prioritizing one over the other. I'm just looking for the lowest locant set. It seems like it got a good number of you. Was that good? Okay, great. Makes sense how that applies. The next one is very similar to the one we did on the top right above. 2 primary ways that you could name this. If you name it straight across from left to right, you can get a 3-tert-butyl hexane. But this gives just 1 substituent on a 6-carbon chain. If instead we number it from the top and then down to the left, we can get a 3-substituent hexane chain. 3-ethyl, 2,2-dimethyl hexane.
Do you always want to try to maximize the number of
Yes, and I feel like after today's lecture, you're going to walk away thinking that that is a common struggle, that you're going to always have to find 2 parent chains and maximize the substituents between the 2 equal length parent chains. It doesn't happen that often, but that is the rule. Yes, we maximize the substituents. Oftentimes, you find 1 parent chain. You just need to decide whether you want to go one direction or the other. For instance, in like these blue cases, go clockwise or counterclockwise. I do want to point out something that often gets missed. Students will write this name as 3-ethyl 2-methyl hexane, or 3-ethyl 2-dimethyl hexane, as if to tell me that the 2-dimethyl clarifies that both methyl groups are on the second position. But I can draw a structure that takes one of those methyl groups off of the second position and places it over here on the 5th position. This is still 3-ethyl, but now it's 2,4-dimethyl. 2,4-dimethyl is a structural isomer to 2,2-dimethyl. So by listing the locant, even when it's the same, when listing the locant every time it appears, we're able to tell apart structural isomerism by having that key indicator. The rule of thumb that I would lean into is if you have a multiplier, you need to have that many locants. Dimethyl should have 2 spots reported, even if it is the same spot. Deal? Okay, I want to go through the other 2 together. So we've got this 6-membered ring that has an alkene and a methyl group. Since I'm on a ring, I can start anywhere I want to. Where might be a good spot to start? At one of the positions with the alkene, since the alkene is the second highest priority functional group of the ones that we're looking at. When I number the alkene, because the alkene consists of a carbon-carbon double bond, wherever I start, I have to count through that alkene. So I can either start at the bottom and count through the alkene to get a methyl at position 4, or I can start at the top and count through the alkene to get a methyl at position 5. Because the alkene is my higher priority functional group, I don't have to say that I'm starting at the alkene. That can be an assumption. So I don't need that locant 1, which means my locant set is comparing putting the methyl at 4 or putting the methyl at 5. Which way should I number this ring? Clockwise in blue or counterclockwise in orange? Clockwise in blue. And the name for this compound is 4-methyl cyclohexene. Would there be anything wrong about calling it 4-methyl 1-cyclohexene or 4-methyl cyclohex 1-ene? No. Be perfectly fine. But it is an opportunity for us to lean into the assumption that we lowered the locant set for the alkene. All right, now we change that structure a little bit and we add an alcohol. Now where do we start? We start at the alcohol carbon. And which way should I number, clockwise or counterclockwise? How do you decide? I'm going to count towards the alkene since I want to make sure it gets its next lowest locant set. So I start at the alcohol, I number towards and through the alkene, and now I get a substituent 6 for my methyl. Could I have gotten a lower total locant set? Yes, absolutely. I could have gotten 1, 2, 3 to describe my 3 components, but that doesn't follow our rules of priority. The lowest locant set for the alcohol, then the alkene, and the name for this compound becomes 6-methyl 2-cyclohexenol. Or we can call it 6-methyl cyclohex-2-enol. Again, we can add the 1 in front of the OL to signify that the alcohol is at position 1. But because it's a ring and we aim to lower the locant set, we don't have to clarify that 1 position. Fun stuff, right? Okay, there is this one last thing that I want to touch on with nomenclature. I think you guys will remember that nomenclature was a system for us to tell apart regiochemistry, how things are connected.
Why didn't you do this one?
Oh, I didn't do that one because I forgot. And I told somebody earlier, it was a bad problem. I was going here for the longest carbon chain being 5 carbons and having that same issue of less substituents versus more substituents. But here you can have a carbon chain of 5 and 3 substituents in a lot of different ways. So I don't know what the right answer is, actually. I wasn't planning on that. But what would be a good answer for this? Right across the middle. In that case, we'll prioritize bromine over chlorine since they're going to tie. So 2 bromo, 4 chloro, 3 isopropyl. Pentane. Is there any other good name for it? I mean, that is the name that I wanted to give it. It's the nicest name. Any other way that we number this, for instance, if I start from the bottom and I go up and to the right, it's going to include naming one of those alkyl groups as a halo substituted alkyl. So in this case, we'd get 2 bromo, 3, and I have to put the parentheses after the comma, 3 1-chloroethyl 4-methylpentane. It's not as nice, and that's not really what I was going for. And I actually don't know which one is the best name. I mean, like vibes-based, this is the best name. But IUPAC, maybe we should call them up and ask them what happens if you have the same parent chain and the same number of substituents. Then do you go for less substituted substituents? I don't know. Okay, thanks for pointing that out. Nomenclature was all under this umbrella of regiochemistry. We talked about how we can tell the position of groups by using nomenclature. This all helps us tell apart things that are structural isomers. Structural isomers have the same chemical formula, different connectivity, a different arrangement of atoms in bonds. But nomenclature can also tell us something about stereoisomers. Stereoisomerism has everything connected in all of the same places, but just arranged slightly differently in space. This has the same bond connections. Unique spatial arrangement. So there's 2 relative descriptors that I want you guys to be familiar with. The first one we see exemplified on the left. There's a structure with bromine wedged on one carbon and dashed on another. The relationship between these two bromines is that they are trans to each other. If those two bromines were shown both wedged or both dashed, then we would call it the cis stereoisomer. All of the same groups are connected in all of the same places, but one of the bromines is arranged differently in space. So these are cis-trans stereoisomers. We use it to describe the relationship of the two groups. Specifically, we can only use this on rings. We're going to look at models for linear chains and cyclic structures, and we're going to show how rings have limited mobility. So when these two groups appear trans or appear cis, they stay that way all the time. On linear structures, freedom of rotation allows groups to look cis and trans at different times. So the second structure that we have, is this a cis stereoisomer or a trans stereoisomer? A cis stereoisomer. Can you draw a trans stereoisomer for this four-membered ring? If I drew both lines dashed, would that become a trans stereoisomer? No. The two groups stay on the same face. They're both dashed. So to get a trans stereoisomer, the top group can become dashed while the bottom stays wedged, or the top group becomes wedged while the bottom becomes dashed. Okay, one last thing that I want to talk about before I send you guys on your break. We're in this world right here of how chemical formulas can express themselves in different ways. The same chemical formula can give different structural connections, and even the same structural connection can give different spatial arrangements. There's a piece of information that we can learn from chemical formulas and from structures. We call it degrees of unsaturation. Saturation here would mean that every atom is bonded to as many other possible atoms, as many other unique atoms as possible. So you have a fully saturated molecule, as many atoms bonded in the molecule as you can. Unsaturation then comes about from atoms doubling up on their bonds to other things in the structure. So two ways that we get unsaturated. And we'll start by looking at this example of propane. If I take two hydrogens away from propane, I can turn two of these carbons into an alkene. So by losing two hydrogens, I now have a pi bond. This means that pi bonds are units of unsaturation in a molecule. If I have a pi bond, I could have had two additional hydrogens attached there. There's another way that I can take out two hydrogens from this structure, and that's if my final product is cyclopropane. In making this ring, I had to remove a hydrogen from both methyl groups, which means I could have had more molecules inside of this structure. That means that cyclopropane and propene are structural isomers of each other. They have the same chemical formula, but their atoms are just connected in different ways. Cyclopropane and propene both have 1 degree of unsaturation. So degrees of unsaturation come from rings and pi bonds. We're going to come back to this idea in Unit 3, but for right now, it's an interesting way to start predicting whether your compound will have rings or pi bonds and what structural isomers can look like for that. Okay, so why don't you guys take a 5-minute break? We'll pick up with this new worksheet at 6:10. And for anybody that's interested, I'll do a little side quest with degrees of unsaturation. Get your blood flowing. Take a break. Yeah.
Okay, so the second one, I drew it like this.
Yeah.
How do we know when it's supposed to be a ring? Because there are carbon chains like this.
Um,
like the
I like there that can exist. Do you know how many hydrogens are in this chain?
3,
Mm-hmm.
4, 5, 6, 7.
Oh, no. 3,
And then another 3.
4.
Yeah.
But this carbon is full. This carbon is full. This carbon is full. And then 5. It's just very strange to have these carbons that have double bonds on both sides. That is actually a group we call an allene group, a carbon that is double bonded on both sides, but it's not very stable.
So it's just not common to have
Or
something
certainly,
like that?
certainly not to this extent, right? Right. We talked about this group, the C6H5 group, being one that I wanted you guys to recognize as what we now know as the aromatic ring.
Got you. Okay.
And so that was a valid guess, and I gave you some credit in the chemical formula for
Yeah.
following the chemical formula.
Right. So just knowing like that C6H5 is how we normally see that.
Yep.
Okay, cool. And then this one, can you explain?
Yeah. How many hydrogens here at that carbon?
At this one?
Mm-hmm.
2.
Good. So it doesn't have a full octet.
Right. That's why it's a charge.
And the oxygen is donating electrons into that empty space where there is not an octet.
Mm-hmm.
And so oxygen has a lone pair. In fact, it has 3. And it's sharing one of those lone pairs to make a covalent bond. Could I show you something?
Yeah.
If all you had done was recopied the structures and then just drew this line, that's what happens. 2 electrons become a covalent bond. And then, of course, there wouldn't be the charges anymore. They neutralize.
So the oxygen literally just bonds.
And do you
there?
see how you actually lost a carbon?
Yeah.
There was a carbon coming off of that chain. Now there's no
Right.
carbon there.
That's true.
And you moved it over here. There was an oxygen bonded to that carbon. Now it's a carbon bonded to that carbon.
Yeah.
So you technically have not lost or gained any atoms, but you've rearranged them in ways that the arrows don't suggest.
No, that makes sense.
So one thing that I would say, if we look at it again, is the oxygen making or breaking a bond?
Making a bond.
Yeah, it's definitely not breaking one because the electron arrow doesn't start at a bond. So there's no bond broken. So there must be a bond formed. Well, how many bonds formed?
Should just be one because there's just one arrow.
Just one. So the rearranging that you had, that takes a lot of making and breaking. There's certainly not enough arrows for that. So do I need to, yeah, now I'm out of my depth. I don't know how to erase.
Now you're okay.
Do I need to do I need to change anything about this part of the structure? Are there any bonds there that need to change?
I was gonna say with the pi bond, isn't that the one that would be most likely to break?
I hear what you're saying,
would you
but there's no
remove
arrow. No arrow touching the pi bond.
Yeah, so you just have to follow it. I can
Follow the arrows.
understand it when I see all of the arrows and I'm like, oh, okay, I can see how to get from here to here.
And here's
But
all the
then
arrows.
When it's like just
Oh.
this, and I was like,
Is it, could you add that arrow? Or like it has to be?
No, I want you to show me
And
what
it-
happens here.
yeah, so he just
I don't
gave
want
me-
you
he
to
just gave me
imagine.
that. He just gave me that, and then I
Yeah.
had to draw that.
So
And
essentially you are just like bonding those oxygens, so it would just
drawing
become,
a
like,
line
one
there just
molecule or
honestly
compound
seemed
together.
way too simple for this problem.
So if this were a carbon, oh, actually, yeah, this is it. That's your structure.
That's literally it.
So you overthought it.
Okay.
Oh.
Sounds about right.
Well, no, I did too, because she was like, wait, what would you have done? And I was like,
Okay, thank you.
Good work. I think this chemical formula is not what I want. Okay, that's better. Okay, I said I was going to do a little side quest on degrees of unsaturation. Here's what I think is cool. If you take this chemical formula and you try to find all of the different ways that you can draw a structure with that chemical formula, there's a lot. And the best way to start is by calculating degrees of unsaturation. Oh, I didn't give you an equation. Well, that would do it. Okay, sorry, here's an equation for degrees of unsaturation. Degrees of unsaturation can be calculated with the 2 chicken rule. Take twice the number of carbons, subtract the number of hydrogens, and the number of halogens, add the number of nitrogens, add 2, and divide by 2. So the 2 chicken rule, because it spells chicken, you multiply by 2, you divide by 2, you subtract 2 times, you add 2 times, you add a 2. There's 2 all over the place. For this chemical formula, our degrees of unsaturation become 2 times 4 minus 9, 0 halogens, 1 nitrogen, plus 2 divided by 2. Okay, 8 minus 9 is -1. Plus 1 is 0, plus 2 is 2, divided by 2 is 1. So this compound has 1 degree of unsaturation. Is that a pi bond or a ring? No, of course not. It's either. So C4H9N could be C4N. And then I've got 1, 2, 3, 4, 5, 6, 9 hydrogens. Okay, but there's no need for my double bond to go between the carbon and the nitrogen, and there's no need for that carbon-carbon double bond to be so close to the nitrogen either. So these atoms are all staying the same, but their structural connectivity is changing. And then I can start changing around how I see that degree of unsaturation showing up in my structure. I could have a 5-membered ring that includes the nitrogen, a 4-membered ring where the nitrogen is coming off. I could have also had a 4-membered ring with the nitrogen inside of it and a methyl group coming off. These are all structural isomers of the same thing. A smaller class inside of that, or an entirely different class, would be stereoisomers, where if I can create different arrangements of having these groups, now I have even more isomers to show. Okay. I think the nice thing about degrees of unsaturation is analyzing it from a compound you already have. You can look at it and count every pi bond and every ring, and you know the degrees of unsaturation. But we'll use it a little bit in Unit 3 to help us make predictions about structures from instrumental data. Okay, I'm going to hand out this next worksheet. Do you guys have questions from nomenclature, isomers? I didn't put this on the worksheet. I'm kicking myself for it now. One thing I always like to do, and one thing that you will see on your unit test for nomenclature, is I will give you an incorrect name, have you draw the structure based on that incorrect name, and then have you fix the name that was given. Thank you, guys. Thank you. So I want to give you an example of what that looks like before we leave nomenclature too quickly. Let's say that you're given the name 1,6-dibromocyclohexane. And your goal is to correct the name. There's nothing you need to change about the name as it is. You need to draw the molecule based on this name. I always like to start with the parent chain. You know that you're going to have a 6-membered ring, so get that parent chain drawn down. Then start adding in the substituents following their locants. Position 1, I have a bromine. And I move my way around the ring. Position 6 gets a bromine. Now, there's not a lot that can be wrong in a name that you can change by changing the structure, or that you can fix by changing the structure. You're going to have to work with this structure. You don't know if that person accidentally read a cyclopentane as cyclohexane. That's not the error that you need to fix. What is the error in this name? It doesn't have the lowest locant set. The locant set should be 1,2-dibromocyclohexane. Okay, we do another. If we take butyl cyclopropane, we start with the parent, that's just a triangle, cyclopropane, and butyl is a 4-carbon chain coming off of it. Now what's the problem? We actually don't need to know where the butyl is, because if we call it 1-butyl cyclopropane, it's still the same. On a ring, there's only just that one position.
Shouldn't the butyl be the suffix?
The longest parent chain is 4, not 3. So this should be described as 1-cyclopropyl butane. I've got a cyclopropyl group coming off of the first carbon on my butane chain. Tricky. Wrong parent chain. The best way to approach these is to draw out the structure and then forget the name that they gave you at all. Don't convince yourself that their name might be partially right. Don't convince yourself that there's something in there that I'm just not getting. Walk yourself through the entire naming process again. Find the parent chain, the longest continuous carbon chain. Identify the substituents. Minimize the locant set. Alphabetize. All right. We have some more learning to do on stereochemistry. In fact, pretty much the rest of the unit, all of Unit 2, is focused on stereochemistry. So this new sheet starts us off with some projections. I like to call these assumed perspective because in order to use these projections correctly, you have to assume a specific perspective. The first that I like to overview is the Fisher projection. The Fisher projection is largely used for sugars, and it's rather complicated with the assumptions that it makes. In a Fisher projection, you will see this straight line carbon backbone. A lot of times I like to think of this as a fish backbone. If you are looking straight down at the fish backbone, it's going to look like a straight line. But there's actually a curvature that is assumed. This is a carbon chain that is pointing away from you as you go up and down the line. Horizontal groups are assumed to be coming at you, both wedged. And you can see this on the diagram that I've given you. You've got this dotted backbone that's going away. Everything else is coming towards you. If you are looking down on this curved apparatus, that means that you could actually be looking at a bond line structure that has this continuous zig-zig. Instead of this alternating zig-zag pattern, we get this zig, 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 zig. From there, everything that was coming towards you is now tipped onto its side, one of them going away and one of them coming towards you with that correct tetrahedral geometry that we talked about. You remember how we said wedges and dashes are always coming out of a vertex on Monday? Here, we've got our vertex being both dashed and wedged. Now we're back to having two things in plane, and a wedged group and a dashed group. We will most commonly work with structures that are in this more of a bond line structure, more of a zigzag formation. But there is an assumed perspective about how you get to those positions. Okay, so let me just ask this. This structure that you have in front of you, how many carbons in that carbon chain backbone? You got 6? 4 hashes, it's not the same as mine. 4 hashes going across and a CHO at the top, an aldehyde group, and an alcohol CH2OH on the bottom. 6 carbons, so this would have some sort of hexane or hexanol parent chain in the nomenclature. What I want you guys to do then is use this as a guide. Use the aldehyde group and the alcohol group. And I want you to add in the alcohols and the hydrogens that are wedged and dashed on this form. I'll give you the first one because it gives you this CHO at the top, the aldehyde, and then it gives an H on the left and OH on the right. When this carbon chain gets flipped down onto its side, this bent carbon chain is tilted. The OH is going to tilt into the board to the right. It's going to be going away from us. The H, as it gets tilted, is coming towards us. So for this first group, we'll see a wedged H and a dashed OH. What I'd like you to do is just take a minute and fill in these wedges and dashes on the rest of the carbons, whether they are H or OH. Take some practice with thinking about those molecules in 3D. Good start. Get a dash on that one too.
Do these two also have?
They'll all have a wedge and a dash on them. Oh, nope, not that one. What good would a lecture on stereochemistry be without some stereochemicals? Okay, this is that idea that I'm trying to get towards you guys. You've got this curved backbone that we are assuming to be observing from this perspective, and then we just write those assumptions in flat lines. Everything going horizontal we assume is coming towards us. Everything vertical we assume is bending away from us. What we're doing at this juncture is just tipping it onto its side. So these groups that are coming towards us, one of them is now going to be pointing away while the other stays towards us. The nice thing about taking this molecule and flipping it onto its side is that everything on the left-hand side, once we flip it, is going to be something that's pointing up out of the plane of the board. Everything on the right-hand side, once we tip it, is going to be something that's pointing back through the plane of the board. So at our first position, we had a dashed OH, a wedged H. At the second position, where's the OH? Also dashed. On the third position, where's the OH? Flips, now it's wedged. And in the last position, dashed. We're not going to work a lot with Fisher projection. Sometimes you see it more in OChem 2. My classes don't see it a lot in OChem 2 either. You see it a lot in biochemistry. There's an assumed perspective to it. The next projection that we'll use to understand, I can't even say to understand. I don't know why this is used, but this is the sawhorse projection. Do you guys know why it's called sawhorse? You ever worked with a sawhorse? Like if you're in shop class or something, that sawhorse is the horse you put your wood on to saw stuff. You can see the sawhorse projection elongates a carbon-carbon bond, and then it takes the three groups that are remaining on both carbons and it just flattens them down. So again, this is a shared perspective. I do want you to notice between the two sawhorse projections that the orientation of the three groups on the front and back carbons is different. On the left, the front carbon has this three groups with one group oriented straight up. On the back carbon has the three groups with one group oriented straight down. The structure on the right has both carbons oriented with one group straight up. So we can actually represent different pieces of information about these three groups and how they're able to rotate through space on this sawhorse projection. But you're really going to use it so little, I'd rather you take it as a chance to practice nomenclature. So to the structure on the left, I want you to draw in fluorines and chlorines and hydrogens, such that you get the name such that you get the compound 1,1,2-trichloro-2-fluoroethane. And for the structure on the right, I want you to provide its IUPAC name. Find the longest carbon chain, find the substituents. Take about 2 minutes to go through those. Well, these other bonds will just go to other things like hydrogens and chlorines and fluorines.
Oh, it can be okay.
Yeah. So you'll just fill in those other groups.
Got it.
So you guys know, when you're filling in the structure on the left, these are the bonds you can draw groups out to. You've got ethane, so you just have a 2-carbon chain. Those will be those 2 carbons. Everything else goes to the other groups.
I think it'd be similar to this.
I think there should be 3 chlorines, but I only see 1.
But it's gonna go on the second one, right?
One of them goes on the second carbon. The other 2 go on the first carbon.
Oh, I see. I was trying to do it.
So you had 1 originally here.
Oh, I see. It's kind of like.
No. No, there are 3 chlorines.
Right.
1 on the first carbon, 1 on the first carbon, 1 on the second carbon.
Okay.
Yes, nailed it. And then this will be a hydrogen, this will be a hydrogen. And we'll draw it in so that we don't assume they are methyl groups. Because if we leave it blank, then it's a CH3.
Can you include that part in the chain?
You should, yeah. We're just taking a perspective on a molecule. So you're still following the same rules. Find the longest carbon chain for the parent. Minimize the locant set. Oh, I knew something looked off. It's F for fluorine, not FL. But I was looking at that and I was like, nope, her first letter is capitalized. Her second isn't. I can't figure out what's wrong with that. Okay, here's one solution that you could have for that 1,1,2 trichloro 2-fluoroethane. I had to draw in hydrogens because I couldn't leave any line blank. That would make me assume there's a methyl group there. So I drew in my hydrogens. You could have rotated these into any combination that you wanted. You could have flipped the front carbon and back carbon. All would have been accurate, but you should have 2 chlorines on one carbon, 1 chlorine and 1 fluorine on the other. This next structure, the longest carbon chain, starts at one of the CH3s, numbers through the sawhorse, and gets me to 6 carbons by the end of that other carbon chain. I've started numbering at the end closer to the first substituent. That's going to help me minimize my locant set. So I get a methyl at position 2 and a bromine at position 3. That comes into my name alphabetically as 3-bromo, 2-methyl, hexane. Did any of you guys struggle with getting that one? What was the struggle? Not knowing how many carbons you were allowed to count through? Not knowing which direction? being thrown off because now you're seeing the molecule from a different perspective than just bond line? Yeah. So I do want you to get familiar with thinking about molecules in different ways, not just in bond line. And these perspectives, they help us get there. Questions before we look at our third type of perspective? This is the one that we'll use far more frequently. This is the Newman projection. And what the Newman projection does it takes the sawhorse projection, which is already looking at a carbon-carbon bond from a slightly exaggerated bond length, and then looking at the other three groups on both of those carbons with a bit of a different perspective. It takes the sawhorse and it shifts it so that you're looking down that carbon-carbon bond with one carbon directly in front of the other. And because of that, you see the three groups on the front carbon and the back carbon, and you can observe how they interact with each other as rotation occurs around that carbon-carbon bond. So we typically depict this by showing an eyeball. Do you see why that's an eyeball? You can see the eyelids opening up and the roundness of the eyeball. Okay. We take this eyeball and we say, sight down a specific bond. All right, well, I'll sight down this bond. You know what? I'm going to make my structure a little bit easier. I've drawn butane, a 4-carbon chain. I'm going to make this a little simpler, and I'm going to show ethane. Ethane is the simplest Newman projection I can draw because ethane only has one carbon-carbon bond. As I sight down this bond, the Newman projection that I get, it has a big circle, which represents the back carbon. And then it has this small circle, which represents the front carbon. I have found students don't always like that the front carbon, the carbon that is quite literally obstructing the view of the back carbon, they don't like that the front carbon is so small and that the back carbon is huge. So sometimes they'll draw this with the front carbon being huge and then the circle for the back carbon. Help them orient themselves a little bit better. But what we'll do is we'll take these three groups coming off of the front carbon, much like the sawhorse projection, and we're going to show them flat on the front carbon. Well, here's the deal. If I grab onto this CH3 group, there's a hydrogen that's coming out of the board towards us and a hydrogen that's going past the board away from us. If I can grab onto those two hydrogens like a steering wheel, then I can pull this molecule out of the plane of the board to show what it would look like as I look down that bond. Or with the things that you have in front of you, with the models that you have in front of you. Take any two of those groups coming off of that second carbon and grab onto them and orient the molecule now with a perspective through a carbon-carbon bond. A hydrogen coming straight down and two hydrogens going up to the right and up to the left. I get this little peace symbol. On the back carbon, I have a hydrogen that goes straight up and a hydrogen down to the left and a hydrogen down to the right. Again, it gets confusing for some people to see it with this perspective, so they'll draw it a little bit differently if they use this big circle in the middle. But we're still showing three groups on the front carbon, three groups just on the back carbon. Here's what I want you guys to do with the remaining 10 minutes. I want you to take the model that's in front of you, and I want you to position it in a zigzag. So that looks like what you have in the middle at the bottom of your sheet. The bond line is in a zigzag. And I want you to pay attention to these colored groups that you have coming off of them. Some of you may only have one colored group. Some of you may have two. But I want you to pay attention to those groups, and I want you to draw them in to this bond line that's already given to you. If it's on the right carbon and it's dashed, draw it dashed. If it's on the left carbon and it's coming wedged, draw it wedged. Then I want you to rotate around that carbon-carbon bond. This is what the Newman projection is really good at showing us. It shows us what happens as a molecule rotates around a bond. I want you to take that zigzag formation and I want you to rotate it from zigzag into zig-zig. And I want you to pay attention to how those colored groups change. So notice that when you go to the right, one of those carbons rotates and the other does not. When you go to the left, the other carbon rotates, the first does not. So you're going to be taking this central point, you're going to rotate one carbon and show what that looks like, and then come back, rotate the other carbon and show what that looks like. What I want you to experience here is the relationship of those wedges and dashes as you rotate around a sigma bond. Look at how the three-dimensional stereochemistry manifests as a molecule is rotating. Then you can take the Newman projections that are already above it, and you can fill in where those groups show up. If you don't want to show this as like a wedge to the word orange, then just name your group. Maybe your group is a chlorine. Maybe your group is an alcohol. Maybe your group is a methyl. Just give it some nature so that you can show it on these structures. Deal? I'll come around to answer questions. So you just start like this, and you've got your CH3, zigzag up to your other CH3. So that's your zigzag conformation. On this carbon, there's a blue group coming towards you, and on this carbon, there's a blue group going away.
Okay, I see. So you want the wedges.
Yep. Then, to get to here, notice your CH3 is going to stay the same, and it's this CH3 that rotates. Now observe the position of the two groups, and then you'll do it the other way. To come here, you've got your zig-zag going this way. Okay. Yep. Does anybody need another one?
This one is either going to be they're both pointing away from you or they're both pointing towards.
It might be different than the one that you just had over there.
So then if you flip it and you look at the carbons, you can see here CH3 and CH3 on the top and bottom.
Good. Perfect.
We don't need to, these are all filled out, right?
No, nothing's filled out.
Yeah, because that's a CH3.
Well, that's just a template. Now you get to, what do you want to call blue? Chlorine? Iodine?
Oh, okay.
Then
Then our chlorine
yeah,
would be up here,
yep,
and it's here.
coming towards you. Yep.
Yeah. Okay, I see what you're saying. Okay, wait, let me do this one.
Like if we switched it.
Kelvin, I'm sorry you didn't get one.
No, I'm good.
We really say this.
Good. Good, good.
If we were, for whatever
See,
reason, to switch.
I don't know like how to do the zigzag one.
Yeah. So let's get it set up so that we have this orientation. I have a methyl group that's pointing down, a methyl group pointing down. I've got this zigzag.
I see. I thought like I had to like take one of those off. Just
Nope.
make this zigzag.
Now, when we want to see the Newman projection, we're going to sight down this carbon-carbon bond. Okay, so here's my zigzag. I have a purple. What do you want to call purple? Iodine? I've got an iodine that's coming towards me, wedged. So this carbon has a wedged iodine, and this carbon also has a wedged iodine coming towards me.
Okay.
Now, when I look at the Newman projection, that's going to be iodine and iodine on the right-hand side.
Okay.
Both wedged, both coming towards me.
Okay.
To get to this one, I want to rotate my carbon chain. I only want to rotate the carbon on the right. I'm actually not rotating the carbon on the left. So I rotate the CH3 up to be a CH3 down. This had a wedged iodine, it still has a wedged iodine. This had a wedged iodine, now it has a dashed iodine.
Okay.
Fill some of that in. I did a lot of words, but now I want to see if you can do the sketching.
I like how we do it like I saw it this thing.
Were we supposed to look at them from a certain angle?
Nope,
Okay.
not really. Good. So you guys started it like this, and you've got your, I'll let you guys see it.
Okay.
You've got your yellow going away, perfect. When you spot down the Newman projection, where's the yellow?
Oh, I see.
You see it? You're saying, oh, but.
Wait, no, I don't see it.
Okay, so we started with this. Nope, sorry. Started with this.
Okay.
This was your zigzag. Here's your zigzag. Now we're going to look down this carbon-carbon bond. So we're looking down this carbon-carbon bond. Carbon in front has a CH3 coming straight down, H and H. The carbon in back has your yellow group, and then an H.
Is that one we would draw like to see the perspective?
Yeah, if you wanted to thicken it, you could thicken it there.
Oh, we're supposed to draw it on this one.
Yeah, so you're sketching what you see here as your Newman projection.
So that would be Y.
All right, now, when you got to this one, I agree that your yellow is going back, but it's going back down out of that vertex. It's not going back up here. Do you see where the line comes together? I want your dashed to come out of it, not through it.
So down. Nice.
Okay, so before we wrap up, what I want to point out, I didn't get the Newman projections drawn up here, but if you started with a zigzag and you rotate one of those carbons into a zig-zig, you guys get what I mean by that, right? I've been told I'm the only one that says that, but I think it is intuitive. When your zigzag moves into a zig-zig, only one of the carbons needs to rotate to do that. This carbon on the left, as I moved to the right, didn't change. And the stereochemistry around it also didn't change. That group that was wedged stayed wedged. But this carbon on the right actually rotated. And as it rotated into a new conformation, a new way of taking up space, the dashed bromine became a wedged bromine. Its stereochemistry is the same, but your perspective of how it's taking up space has changed as a result of a rotation. So what was dashed now looks wedged, and we can do the same thing in reverse. This wedged group is now the only one to rotate, and that dashed group becomes wedged. On Monday, we'll start by filling out, or I'll show you what these Newman projections look like, but those Newman projections will help you see that things that are wedged and dashed are on opposite sides of a Newman projection. Things that are dashed and dashed or wedged and wedged, those are on the same side of a Newman projection. Again, giving us terms like cis and trans, or syn and anti. We're going to talk about chairs, rings on Monday as well. And then we're going to dive into some more information on stereochemistry. So bring these worksheets back on Monday. We'll go through the backside. Have a good weekend. Oh, by the way, when you get into active, you have enough ground to cover on both section 3 and section 4 of active. So I taught nomenclature as kind of one big thing, but active goes through the nomenclature separately as linear chains and rings. So start making some progress in 3 and 4 over the weekend. See you guys on Monday.